Hi everybody, Justin here from chemistrynotes.com, and today's video is about the two types of intermolecular forces. So there are two types of intermolecular forces that we're going to talk about today. The first one is called dipole-dipole forces, and let me give you a backdrop on dipole-dipole forces. Dipole-dipole forces only occur between polar molecules. Okay, now the second one is called London dispersion forces. So the first one, dipole-dipole forces, which only occur between polar molecules. And the second one is London dispersion forces. Sometimes London dispersion forces are called van der Waals forces or London forces. Now, London dispersion forces occur between all types of molecules. So the only requirement for this is that the molecule, the atom, or the ion have electrons. So this occurs between all types of molecules, but these are the only intermolecular forces holding nonpolar molecules and noble gas atoms together. So if you're a polar molecule, you have dipole-dipole forces and London dispersion forces. If you're a nonpolar molecule, you have only London dispersion forces. All right, so let's take a closer look at both of these two types of intermolecular forces. We'll start with number one, dipole-dipole forces. Now, it's important to remember that intermolecular forces are not nearly as strong as bonds. Okay, so dipole-dipole forces are only 1% as strong as covalent or ionic bonds. Okay, intermolecular forces are not nearly as strong as intramolecular forces or bonds. Okay, and we talked about that in the previous video. All right, so let's do an example exhibiting dipole-dipole forces. I'm going to take the polar molecule hydrochloric acid, or HCl, and I'm going to draw 4 HCl molecules. Okay, so the way I've drawn them here, you can see that the chlorine is more electronegative than hydrogen, so we have our little arrow-looking dipole moment. I'm also writing the partial negative and partial positive charges. So those little double-headed arrows that you see, that would be an example of a dipole-dipole bond. It is an intermolecular force in that it's an attractive force between molecules. And then the 4 molecules I've drawn here, this actually goes on in all directions and in 3 dimensions, right? So I'm drawing an arrow there, a squiggly arrow to the dipole-dipole interaction, that little double-headed arrow that attracts the hydrogen end of one molecule to the chlorine end of a separate nearby molecule. So that's an example of a dipole-dipole force. A special type of dipole-dipole force is called hydrogen bonding. So we're on page 2 of our notes here, and at the top of page 2 of our notes, I want to talk a little bit about a special type of dipole-dipole force called hydrogen bonding. It works in the exact same way, in the exact same manner as the example I just did for hydrochloric acid, but hydrogen bonding has a few requirements. Hydrogen bonding occurs in polar molecules, and one of the requirements is that the polar molecule has to have an OH bond, an NH bond, or an FH bond. Okay, so OH bonds and NH bonds are quite common. We see hydrogen bonding with them quite a bit. FH bonds also exhibit hydrogen bonding. Now, hydrogen bonding, which is a particular type of dipole-dipole force, is stronger than a regular dipole-dipole interaction for 2 reasons. Okay, so stronger than a regular dipole-dipole interaction, and then if someone asks the question why, well, we would say the following. We would say that hydrogen bonding is stronger than a regular dipole-dipole interaction or a regular dipole-dipole force for 2 reasons. And we're going to list those reasons here. Okay, so A, because hydrogen is small okay, because hydrogen is small, it's going to allow for dipoles to be in very close proximity to each other. It's kind of like two magnets, right? The closer the magnets are, the stronger the interaction between the two. Same thing with hydrogen being so small. And then B, we actually mentioned the fact that the magnet, if you will, is bigger. So let's break this down. Hydrogen bonding is stronger than a regular dipole-dipole interaction. A, because hydrogen is small, allowing for dipoles to be in close proximity. And B, because nitrogen, oxygen, and fluorine are so very electronegative, that means that the dipole-dipole interactions are going to be that much stronger, okay? The dipole-dipole interactions are highly polarized, okay? So the magnet example is a good one. The magnet gets closer, stronger interaction between the two, okay? If the magnets are highly polarized, again, that would be B, stronger polarity, okay? Stronger interaction. Water exhibits hydrogen bonding. So at the top of page 3 of our notes, let's talk about water, H2O. So I'm drawing a Lewis structure for water, and we can see that it's polarized towards oxygen. Oxygen is more electronegative than hydrogen. So we have our delta pluses, our delta minuses. And I'm now just going to draw a grid. Maybe you just want to assume this is a liquid sample of water molecules I'm drawing. So I've drawn 5. Let's draw a 6th one right here in the middle row on the right. All right. Now I'm drawing interactions between the electronegative oxygen on one neighboring molecule with an electropositive or a delta plus hydrogen on a nearby molecule. Okay, that's called a hydrogen bond. Now it's not a real bond in the sense of an intramolecular bond, but we'll mention a few notes here in a second. But I just want you to see how this causes the water to be aggregated and collected together, and this is why water molecules are so hard to break up. It requires such high temperatures to melt ice and to boil liquid water, right? So hydrogen bond is not really a bond, but it's instead an intermolecular force. It's a special type of dipole-dipole force, a stronger version. And if you look at any of the water molecules I've drawn in my little example, each water molecule makes 4 hydrogen bonds to neighboring H2O molecules. So you see that a delta minus oxygen on one molecule is going to be attracted to 2 of the delta plus hydrogens on nearby molecules of water, right? All right, so here's a sample question that kind of tests us on whether or not we understand hydrogen bonding versus a regular dipole-dipole force. Example, H2O has a melting point and boiling point of 0 degrees Celsius and 100 degrees Celsius, respectively, while H2S has a melting point and boiling point of negative 82 degrees Celsius and negative 60 degrees Celsius, respectively. So why does it require so much more energy in the form of heat to melt water and to boil water as opposed to H2S, which has a very, very similar structure and molecular geometry? Well, the answer is that the requirement for hydrogen bonding, you had to be an OH bond, an NH bond, or an FH bond. And SH is not one of those, okay? So the H2S molecule doesn't undergo hydrogen bonding, but H2O does, all right? So at the top of our new page of notes here, it says on that first bullet point, H2O molecules are aggregated tightly to each other, okay? They're collected together, aggregated tightly to each other by very strong hydrogen bonding, okay? H2S, on the other hand, those molecules are not, okay? So there's the difference. The stronger the intermolecular forces, okay, the harder it is to melt that substance or to boil that substance. Because to do that, we've got to disrupt the intermolecular forces. So let's recap. It says H2O molecules are aggregated tightly to each other by very strong hydrogen bonding. H2S molecules are not. The stronger the intermolecular forces, the more difficult it is to separate the individual molecules from each other. And by separate, I mean maybe we're melting or maybe we're boiling, all right? So what happens is this results in a higher melting point for H2O and a higher boiling point for H2O relative to H2S. All right? So H2O, H2S, very similar Lewis structures, very similar molecular geometries, but the properties that their melting points and their boiling points are so much different is because of hydrogen bonding. Now, H2S molecules are held together by regular dipole-dipole forces. And of course, both H2O and H2S also have London dispersion forces because the only requirement for London dispersion forces is that you have electrons. All right. Speaking of London dispersion forces, that is number 2. I want to talk about number 2 now. So there's 2 intermolecular forces today, right? There's dipole-dipole forces, of which a special one is hydrogen bonding. And then there's number 2, London dispersion forces. Sometimes called London forces, sometimes called van der Waals forces. I'll call them London dispersion forces, all right? Now, they're abbreviated LDF, although I admit sometimes I'll call them LDF forces. So in a weird way, I'm kind of saying forces twice, but the abbreviated LDF. Now, in nonpolar molecules, that's where we don't have dipole-dipole forces, right? In nonpolar molecules and then in noble gas atoms, these LDF forces are especially important because it's the only intermolecular force. It's the only intermolecular force holding a sample of molecules or a sample of noble gas atoms together. All right? So in nonpolar molecules, LDF forces are especially important because it's the only intermolecular force. All right, so how do London dispersion forces work? How can something that's nonpolar be attracted to something else that's nonpolar? How are we going to get them to aggregate? Well, it's all about 2 phrases, an instantaneous dipole and then another phrase called an induced dipole. So we're going to go through a little drawing here, a little schematic of how this would work. All right, kind of a step-by-step. So LDF forces are caused by an instantaneous dipole. So I've underlined that twice to emphasize it. LDF forces are caused by an instantaneous dipole or an instantaneous polarization that can occur randomly at any given instant within a nonpolar molecule or atom. All right. So basically, like you have a certain number of electrons in a nonpolar molecule, right? And at any given time, you could have an unequal distribution within that molecule, just randomly. All right. So that's what we're getting at here. So here I have an example where I have H2. And in the first one, I have H2 written as nonpolar, where it's behaving as it should. That's how H2 normally is almost all of the time. But at any given instant, for some reason, maybe of those 2 electrons in that HH molecule, at some instant, because they're shared, right, we could have 2 of them on this side and none on this side. That creates an instantaneous, for a split-second, dipole. All right, and then we have a partial positive and a partial minus that occurs for just a fleeting moment. All right, so the instantaneous dipole occurs randomly, and H2 gets polarized as 2 electrons are no longer spread out equally. Now, this polarization will in turn induce a dipole in a neighboring H2 atom that's behaving itself. And by behaving itself, I mean it has a 0 above it. It's completely nonpolar at that time. But if you have one molecule that is instantaneously polarized for a split second, that's going to induce neighboring molecules to polarize themselves. Why? Well, if you have a partial positive and a partial minus, even for a fleeting moment, what's it going to do? Well, just look at the drawing I've drawn here, right? You see the delta minus on the hydrogen, right? When it interacts with a H2 molecule with a 0 above it, which is behaving normally, if you will, it's going to push electrons away from it because electrons repel electrons, right? Negative, negative are going to repel. like opposite ends of a magnet. So what happens is I've pushed the electrons away in my molecule number 2, my H2 number 2, and all of a sudden I've got an intermolecular force. Now imagine that on a grander scale, and we have a London dispersion force for H2. Okay, and it works like that for anybody who has electrons. So the more electrons you have, right? H2 only had 2 electrons. But if I have something that is enormous or large, there's going to be more electrons that show in that molecule or in that atom. And the more electrons you have, the easier it is to have a disparity between the two sides. Right? The easier it is to be off. All right? Or not off, but to be lopsided where more electrons are on one side versus the other at that instant moment. All right, so in other words, the previous example only had 2 electrons, right? That was H2 on the last page. The larger the molecule, the greater the Ldf forces. Why? And I've underlined why. Well, because large molecules have many electrons, and it's easier for an uneven distribution of electrons. Okay, so the larger the molecule, the larger the number of electrons. The larger the number of electrons, the easier it is to get an uneven distribution to occur. In other words, it's much easier for quote-unquote instantaneous dipole to occur. All right? So in the next video, we're going to talk about the liquid state, and we'll get into that one right now or when you're ready. Thanks.